This is Chapter 7, Chemical Quantities and Reactions. The first thing that we're going to talk about is the mole. So the mole is not something that you would find on someone's body, but it is a unit of measurement in chemistry. If you have ever used the word a dozen, or the phrase 1 dozen, to talk about 12 eggs, then you are familiar with how chemists use the word mole. We're going to learn about what a mole is and how to use it, and if you notice that all of these over here, they look familiar to us, hopefully. Not maybe the words sheets, ream, and gross, but the fact that they are presented as equalities should make you think about chemical conversions. So we're going to be doing conversions. I'm just giving you another conversion factor. We're not going to use it in a way that's any different than you already using conversion factors. It's just going to be a new conversion factor. So Avogadro's number is named after Amedeo Avogadro, who came up with this idea, but that a mole is equal to 6.02 times 10 to the 23 things. Now, on your periodic tables, I think that you have 6.022, and so I'll be using 6.022 times 10 to the 23 for things because changing that to a 0 here is actually rounding a really big number. And so if you can remember 6.02, you can remember 6.022 times 10 to the 23. Regardless, you don't have to memorize it because it's on your periodic table. And so any mole, a mole of anything is 6.022 times 10 to the 23 things. And so a mole of books would be this many books. And this number is very large, as you can see here. This is a very, very, very big number. It's a sextillion number. And so why would we use such a big number when we're talking about things in chemistry? Well, we're counting tiny little things like atoms, molecules, and ions, and because they're so small, we need a really big number to count them, because counting each individual doesn't make a lot of sense as far as how they come. If you have 1 mole of something inside of that small amount of sample, which you'll see in a second is a very small number, you have this many particles of that thing. So if you have a mole of an element, elements can break down into atoms, and elements can also break down into molecules. So there are 2 types of elements that exist as atoms, like carbon, sodium, and then you have your elements that exist as molecules. Do you remember that your elements that exist as molecules are supposed to know? You have your diatomic elements. And these guys exist as molecules. And so if you're talking about hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, or iodine, these 1 mole of fluorine would be equal to 6.022 times 10 to the 23 fluorine molecules. And if you wanted to find the atoms, you'd actually have to do 1 more little conversion because there's twice as many F atoms in 1 F2 molecule. So be careful when we're talking about elements. You can either have atoms or you can have molecules of the same element. And if you're talking about a diatomic element, the mole that you're talking about, the unit, the smallest unit that you're going to break that into is actually a molecule. So here's just a nice table for you to help you remember this. A mole of aluminum would be atoms, sulfur would be atoms, but water, the smallest unit of water, is a molecule, and the smallest unit of vitamin C is also a molecule. Look at the ionic compound. sodium chloride. The smallest unit is called a formula unit. We don't call the smallest part of an ionic compound a molecule because a molecule indicates you have covalent bonding there. So remember, we would want to kind of maybe to this list add 1 mole of a diatomic something is 6.022 times 10 to the 23 molecules of that diatomic substance. I keep messing up the U there. So Avogadro's number, as you can see in your list here, can be written as a conversion factor because all of these pieces equal each other. And you know how to use a conversion factor. So don't let this be something scary because it's a big number. It is actually just a conversion factor. You can use it either way here at the bottom with the mole on top and the number and the particles in the bottom, or the mole on the bottom, particles on top. And the particles depend on what you're talking about. So we're either talking about atoms. You can talk about molecules. Now when I do molecules, I will abbreviate molecules as cules. I cannot abbreviate molecules as mole because that's not the same thing. That's what we're measuring, right? A mole. You can also have formula units. And you can abbreviate those formula units. Or you can have ions. Right? Any tiny little particle, you should think, I'm going to be using Avogadro's number. Avogadro, not avocado. And so let's look at some practice. Avogadro's number is used to convert moles of substances to particles. How many carbon dioxide molecules are in 0.50 mole of carbon dioxide? Now the smallest unit here is going to be molecules because carbon dioxide is a covalent compound and the smallest unit for that covalent compound is in molecules. And so I'm going to first find a conversion factor just like we've done in any other conversion problem and decide how I'm going to use that. If I want to know how many, and I'm going to do my abbreviation of cules of CO2 are in 0.50 mole of CO2. And you can also abbreviate the word mole, M-O-L, just drop the E. I don't know why chemists were too lazy to do the E, I guess. But it is an appropriate thing to drop the E. You're going to have, this is your starting place. Now I need a conversion that links my molecules to my moles, and I know Avogadro's number. 1 mole of anything, and we could put in CO2 here, is equal to Avogadro's number of particles. The particles that we want here are the molecules. And so we need one conversion to link these two things. Right, so I will place these in your conversion factor, your dimensional analysis, just the way we've done before. So starting with the moles of carbon dioxide, now the moles of carbon dioxide need to go on the bottom. For every 1 mole of carbon dioxide, I have 6.022 times 10 to the 23 molecules of carbon dioxide. My carbon dioxide moles will cancel, and my molecules of carbon dioxide are left to be my final answer. Make sure that when you're doing this in your calculator, that you're using correct notation for whatever calculator that you are using. If we're using our class calc, then we should be using 0.5 times 6.022. Hold the equal sign down to get your times 10 to the, and then put your 23 on the end, and you get an answer of 3.011 times 10 to the 23. We need how many sig figs? If you look at your given information, there are how many? There are 2 sig figs here, so I need 2 sig figs, and so I will have 3.0 times 10 to the 23 molecules of CO2 as my final answer here. So here's a multiple choice question for you if you want to pause and give it a shot. Alright, back from that break. Hopefully you worked on this on your own, and now you'll see what you get. What are the number of atoms? And so I'm looking for atoms if I have this many moles of aluminum. So I want to know how many atoms are in 2.0 moles of aluminum. And we're talking about aluminum in both cases, so you can either put the Al for both sides or you don't have to, as long as we're talking about the same thing in both cases. Now I know I have a conversion. 1 mole of something is equal to 6.022 times 10 to the 23 of that thing. In this case we're talking about atoms. And I can go ahead and start my conversion. 2 mole of aluminum, mole goes in the bottom, followed by the 1, is equal to Avogadro's number of atoms. Moles cancel, atoms are left, and we have 2 times 6.022 times 10 to the 23, and we get 1.2 times 10 to the 24 atoms of aluminum as our answer. Just the same as we've been doing before, it's just a new conversion, nothing fancy, just put it in the calculator. So if you want to, go ahead and pause and try again. If not, you're welcome to kind of continue on. If you did pause and you want to work through this, we want to know how many moles are in 1.8 times 10 to the 24 atoms. Oh wait, so for this one we had an answer and it was option C, sorry. This is again another multiple choice. I know that 1 mole is equal to 6.022 times 10 to the 23 things, and the thing we're talking about here is atoms. And so if I'm starting with 1.8 times 10 to the 24 atoms, atoms go on the bottom. The number that goes with atoms is Avogadro's number. Avogadro's number always goes with the small particle. It never goes with the mole, so be careful with that. Your atoms will cancel, and we're left with moles, which is what we want, so now we can do our math. So I will be careful here and maybe use parentheses, because I want to make sure that my calculator puts the Avogadro's number on the bottom. And so I will say divided by, open parentheses, 6.022 times 10 to the 23, and then I'll close parentheses. Now your class calc will automatically put things on the bottom when you divide, but be careful because some other calculators can put that times 10 to the 23 on the top and kind of separate it out. So be very careful with how you use this. And you should be getting how many sig figs? 2 sig figs, 2.989. If I want 2 sig figs here, take a second, think about how you would do that. If I want to round this up, it will be 3.0 moles. And so my answer is option, not C, option B. Alright, moving on. Moles of elements in a formula. So if I have a formula, I can actually kind of do, I can look for different numbers of atoms in that formula using Avogadro's number, but also comparing those atoms to the other atoms inside of the formula. And so if you're looking at the formula for aspirin, here this molecular formula, and that's what we call this guy, molecular formula, you have 9 carbons, 8 hydrogens, and 4 oxygens in 1 molecule of aspirin. So how can we write this out? The subscripts of the chemical formula show you the relationship, the ratio, okay, that's the relationship of the atoms in the formula. And they also tell you the moles in 1 mole of compound. So in 1 molecule of aspirin, there are how many atoms of carbon? Well, there are 9 atoms of carbon. And there are how many, let's not do equals, maybe, I mean you can do an equal sign, but I'll just also show you with arrows. how many atoms of hydrogen? Well, there are 8 atoms of hydrogen, and there are 4 atoms of oxygen. Now, because Avogadro's number works the same for atoms or molecules, we can actually turn these words, molecules and atoms, into moles. They can all be moles. And so in 1 mole of aspirin, you can have 9 moles of carbon and 8 moles of hydrogen and 4 moles of oxygen. So I want to call this something. We're going to call this a mole to mole ratio. And we're going to see this in a few different places. We're going to see it here using subscripts, which are the little numbers at the bottom, the subscripts like submarine, the subscripts. And we're also going to see it in balanced chemical equations a little later. But you can turn these into equalities for whatever you want. And so for an example, if I have this aspirin, I want to know how many atoms of oxygen are in 0.150 mole of aspirin. Let's look at some conversion factors. So I know that in 1 mole of aspirin, how many oxygens are there? Well, in 1 C9H8O4, there are 4 oxygens. And so there are 4 moles of oxygen by default, because I can turn these molecules and atoms into moles, because Avogadro's number works the same for all of them. So I can use this mole to mole ratio that I see given to me by my subscripts. And I want to know about number of atoms though, not moles of oxygen. So now I have a conversion to get me to mole of oxygen, but I need to go all the way to atoms of oxygen. So anytime I see a small tiny particle unit, I need to remember Avogadro's number. But this time I am going to write what I'm talking about. I'm talking about oxygen. And so Avogadro's number is going to be for atoms, because I'm talking about an individual element. Now, I'm not talking about oxygen by itself, because oxygen by itself, of course, would be diatomic. I'm talking about oxygen inside of another compound, and that is not necessarily diatomic. So now I have a mole of oxygen to mole of aspirin conversion, and then a mole of atoms to oxygen conversion. So if I start with 0.150 mole of aspirin, how many atoms of O are in 0.150 mole of the aspirin? And I can check my conversions to see that I have them all. So I have my aspirin to start, and I know that in 1 mole of aspirin, there are 4 moles of oxygen. Now notice here it's really important that I put my unit in, that I put the substance in, because the unit's the same. So I can cancel moles with moles just fine, but I cannot cancel moles of aspirin with moles of oxygen. So the moles and the aspirin, now they go together as 1 unit. And so I've got moles of oxygen left to continue my work. And I want atoms though, so now I need to cancel moles, and I know that for every 1 mole of anything, I can use Avogadro's number to get me little tiny particles of that thing. I can cancel the mole of oxygen with mole of oxygen, and I'm left with atoms of oxygen here. And so to put this in my calculator, 0.15 times 4 times Avogadro's number, how many sig figs? Don't use the 4 as a sig fig because it's a counting number, it's a ratio, so we're going to be using the 0.150 as sig figs, and that is 3 sig figs, so 3.61 times 10 to the 23, and the unit is atoms, and the substance is oxygen, and I want to make sure that I'm very clear about all of those pieces. Alright. So another conversion that we can use is called molar mass, and molar mass of an element is how many grams are in 1 mole of that element. And this is going to be what you can find in the periodic table, where we talked about how you can find that atomic mass number, or the average atomic mass of each element, this is going to be equal to 1 mole of that substance. So this number can be either the AMU, atomic mass unit, or it can be the grams per mole. And every time you see a per, you should think, I can use that as a conversion. And so I can write this as 1 mole of sodium is equal to 22.99 grams of sodium. And this is a conversion that, again, I can use the same way I use every conversion. So here it is being used as a conversion. This is carbon's molar mass. You can use it with moles on top or with grams on top, just like with any other conversion. Again, on the periodic table is where you'll find all of your molar masses. I would love for you to give me 2 decimal places. So please round to the hundredths place. Sometimes periodic tables will give you more than that, which is fine, but don't ever do less than the 2 digits after the decimal. So at least 4 sig figs, or 2 digits after the decimal. So here's what 1 mole looks like of certain things. And so 1 mole of sulfur. 1 mole of sulfur weighs about 32 grams. A mole of iron weighs about 55 grams. And so thinking about what a mole is, you can look at kind of how dense, right? How big or how small these particles are. The sulfur, it looks like more, right? But the iron is more dense. And so you can kind of think about maybe the size of the particles, the space between the particles. But every substance has a different mass, because every substance has a different size, has a different number of protons and neutrons. When you know that the protons and the neutrons, they are what give us that AMU number, and so they're what give us also that gram per mole number. So here you have sodium chloride, that's 58 grams is 1 mole. And these other ones I'm not sure off the top of my head, but they're obviously more per mole because they've got more atoms in those formulas. And so you know that if this is equal to 1 mole, then this is also equal to 6.022 times 10 to the 23 atoms of sulfur. And so now we've kind of connected a couple of things. I can go into the lab and I can measure the grams, and because of molar mass, I can find the moles, and because of Avogadro's number, I can find how many individual particles there are of that substance, which is really cool because I can tell you, hey, go get me 6 times 10 to the 23 atoms of sulfur, and you can go weigh 32 grams of it, and you have that amount. So how do we calculate the molar mass of something that is a little more complicated than just one element? So let's look at this, lithium carbonate. And so lithium carbonate, we're going to kind of do the same thing we did with counting our valence electrons and kind of split everything up and then add it. And so the first thing I want you to do is make a list of all the elements that you have, all the elements that you have inside of your compound. We have lithium, we have carbon, we have oxygen. The lithium, how many lithiums do I have? I have 2 lithiums. Each lithium, if I look on the periodic table, weighs a certain amount. And so if we look on the periodic table, we see that lithium is 6.9, I think it's 6.97, let me check. 6.94. Carbon, I have 1 carbon in this compound because a no subscript means 1. So 1 carbon is 12.01. And I have 3 oxygens, so 3 oxygens is 16.00. Now your periodic table may have 15.998, and it's fine to round that to 16.00. So we're going to do a quick little bit of math here. So 2 times 6.94, 13.88, 12.01 times 1, And then we have 3 times 16 is 48.00. Don't lose those 4 sig figs digits after the decimal place here. Now we're going to do like we did with valence as well as add them all up. So I have 9, 8, 13, 4, 5, 6, 73.89 grams per mole. And so I can actually practice writing this as a conversion. So in 1 mole of lithium carbonate, I will be able to weigh out 73.89 grams of lithium carbonate. Why don't you try this one and then press play again to see if you get it right. So for this one, we're going to use carbon, hydrogen, and oxygen. I have 2 carbons weighing 12.01 each, so that's 24.02. I have 6 hydrogens weighing 1.01 each, that's 6.06. And I have 1 oxygen weighing 16, which is equal to 16. This gives me 46.08 grams per mole. So, again, as you know, you can use this as a conversion factor. Here are some examples of how you can do that. So let's give it a try. A box of table salt contains 737 grams of sodium chloride. How many moles are present in the box? So I have how many moles of sodium chloride are equal to 737 grams of sodium chloride. So I need a conversion to take me from grams to mole. I know if I see moles, I see mass, I'm going to use molar mass. Mass is grams. You have to know that this is mass. And so I have sodium chloride, that's in the formula is NaCl, and I know that 1 sodium is 22.99, and I know that 1 chlorine is 35.45, and so I know that the total of sodium chloride is 58.44 grams per mole. And I can rewrite that 58.44 grams of sodium chloride equals 1 mole of sodium chloride. And so now I have a conversion I can use, and 737 grams of sodium chloride. Grams need to go on the bottom, so the grams that go for my molar mass are 58.44 grams of sodium chloride is equal to 1 mole of sodium chloride. They want moles, so I have what I want, canceling my grams, and this gets me 737 divided by 58.44, which is 3 sig figs, 12.6 moles of sodium chloride. And then you could go from there and you could figure out how many atoms of sodium or how many formula units of sodium chloride that is. So here's another example if you want to pause and give it a shot. If not, we're doing plenty of work in class on it. Sample of water has a mass of 59.8 grams. How many moles of water in the sample? So how many moles are equal to 59.8 grams? And this is all of water. So I need to do a molar mass of water. When I do that, I should get 1 mole of water is equal to 18.02 grams. Let me know if you have questions about how to get the molar mass of that. And I can use this as a conversion. I can say 59.8 grams of water. Grams are going to cancel, so they're going to go on the bottom. 18.02 grams of water is equal to 1 mole of water. And I can take my 59.8 divided by 18.02. 59.8 divided by 18.02. Well, 59.8 divided by 18.02. Sorry, my fingers were messing up the numbers. 3.32 moles of water is my answer here. So here's a nice little chart to help you remember what you can go back and forth from for moles and mass and particles. We can use the subscripts to go from either atoms and molecules or moles and moles. And we can use the molar mass to go from grams to moles and back and forth. So moving forward, now we're going to be looking at the equations for chemical reactions. And this is going to also be in our lab, so I'm not going to go over too much in this. We're going to do some work in the lab here. But a chemical change is when a substance is converted into a new substance. We talked about chemical or physical properties and chemical or physical changes before, so these are all going to be chemical changes. For example, the tarnishing of silver. We have silver that pulls in sulfur that tarnishes it. So evidence of a chemical reaction. Iron rusting is a classic example. Takes on oxygen from the air, it oxidizes, and it turns into iron. This substance here, give a practice naming that. That is iron 3 oxide. So writing a chemical equation, we write reactants on the left, we write products on the right. You always write reactants on the left and products on the right with an arrow in the middle, not an equal sign in the middle. You can also tell me the state of matter of each of your reactants and products by putting little letters in parentheses behind the formula. So here we have carbon and oxygen reacting to make carbon dioxide. This is what happens when you burn like this coal here. So a couple things to look at when you're using a chemical equation. An arrow separates the reactants from the products. Reactants are on the left, products are on the right. Multiple reactants or products are separated by a plus sign. The delta sign indicates heat if it's over the arrow. And then you can use solid, liquid, gas, and aqueous to talk about the type of substance that you have. And the type of substances that we're going to use are in this chart here. Solid, liquid, and gas are pretty, you know what those states of matter are. And aqueous means it's dissolved in water, which is where we get the aqueous from. Most things that we use in the lab are aqueous. So dissolved in water. So if we're going to be using chemical reactions, we have to make sure that we are using balanced chemical reactions. So if I put 2 hydrogens in, I got to get 2 hydrogens out. If I put 2 oxygens in, I got to get 2 oxygens out. And so in this slide, they're kind of showing you a visual representation of this. If you go into Canvas under Chapter 7, you will see something called a balancing simulation. You may want to click on that and go through that balancing simulation. We'll also look at it in class as well. But it's a really good practice, and it's got little games that can kind of help you with that balancing. But essentially, you want to make sure that the amount of hydrogens you put in is equal to the amount of hydrogens you get out, and the amount of oxygens you put in is equal to the amount of oxygens that you get out. That has to be true because you cannot create or destroy matter according to the law of conservation of matter and mass, and so therefore this has to occur. So how we balance things is we put these numbers in the front to have things add up to be the same on both sides. And so 2 hydrogen molecules equals a total of 4 hydrogens because it's 2 times 2. And then I have 1 oxygen, which is 2 oxygen atoms. And then I have 2 water molecules, which is 2 times 2, which is 4 hydrogen atoms, and 2 times 1, which is 2 oxygen atoms total. So I'm adding up the total reactants and products on both sides. So how can I do this without looking at a picture, without drawing things, or without using maybe the simulation that you checked out on Canvas? I'm going to show you how I solve these by using a T-chart. And so a T-chart is just that, is a chart. Oops, I'm going to move that down a little bit. It is a chart that it looks like a T. And I would like for you to put the T directly under the arrow, not doing it off to the side or anything. And the first thing we're going to do is we're going to take inventory. And so I want you to look at each atom or polyatomic ion on both sides, reactants and products. So on the reactant side, I have aluminum and sulfur. I have 1 aluminum and I have 1 sulfur. On the product side, I'm going to copy paste my list So make sure it stays in the same order on both sides, even if it's not in the same order, actually written on that side. You want the T-chart to have the same order. So I have 2 aluminums and I have 3 sulfurs here. So I need the numbers at the bottom under the T to be equal on both sides. You cannot just change this and say, 2, 3, and I'm done. Because this number down here represents actually how many you have in the formulas at the top. This T-chart area, this area here, is your work area. It is not the answer to the balanced chemical equation. And so what can I do? I can play with numbers in front of, and only in front of, these compounds. I cannot change the subscripts. You just spent a whole chapter trying to figure out what subscripts go where based on charges and ionic and covalent compounds, right? So don't change that. We want to change how many of them we have. If we have one of them, think about a mole, right? I have billions and billions of them. And so let's just start with the aluminum because that's the very first thing. So if I need 2 aluminums on the left side, what number can I put here times 1 to give me 2? Well, I can put a 2 here. So we gotta start somewhere, so let's just throw a 2 here. So 2 aluminums. Now 2 times 1 is 2, so I change it down here. Always change it at the top up here before you change it down here. Now let's look at sulfurs. I need 3 sulfurs. And so what can go here times 1 to give me 3? Well, stick a 3. 3 times 1 is 3. Now I have a balanced chemical equation because my 2 is equal to 2 and 3 is equal to 3. This is a balanced chemical equation. What number goes here in front of the aluminum sulfide? You can put a 1 here if you want to, or you can leave it blank. Either way. But that is how you need to think about balancing chemical reactions. So for now, just tell me how many atoms of each element are on the reactant side and how many atoms of each element are on the product side. So pause if you want to and check that out. Let's take a look. So how many phosphorus are there? So let's do our T-chart. So how many phosphorus on the left side? 4. How many bromines? 12. 6 times 2. How many phosphorus? 4 times 1. How many bromines? 4 times 3. 12. So this is balanced. You can check to see if an equation is balanced by doing this. Down here, I have aluminums, and I have 2 of them. I have iron, and I have 2 of them. I have oxygen, and I have 3. On the right side, I have aluminum, and make sure you're copying and pasting this list instead of going in the order that it's seen. I have 2 aluminums. I have 2 irons, and I have 3 oxygens. So both of these equations are balanced. Make sure you can quickly do that. You don't have to do a T-chart every time. If you get used to doing it in your head, do it in your head. Alright, so now we're going to practice actually taking a word problem, writing an equation, and balancing it. So here's where everything's going to start coming together. Solid iron, this is a magnetite, I think. Fe3O4, it's kind of a weird thing. So we've got Fe3O4, and it is a solid, so we can put a little S after it. Reacts with, so reacts with means we're going to put a plus sign, hydrogen gas. And so hydrogen gas is actually diatomic, and so I'll write H2, not just H. And it is a gas. To produce means we're going to make a product, so products go on the other side of the reaction. Solid iron, so iron is just S. Do not give iron a charge here, it is just normal iron. I'll say iron ion if I wanted a charge. And water. And water should always be assumed to be liquid, unless you're told that it's steam, water vapor, or solid water ice. Now, you have little areas that you can play with for balancing in the front, so I put some lines there to help me remember that. So I need to balance this now. So I will make my T-chart. I have iron, I have oxygen, I have hydrogen. Copy, paste my list from left to right. And I'm going to take my inventory. I have 3 irons, 4 oxygens, and 2 hydrogens. I have 1 iron, 1 oxygen, and 2 hydrogens. I need these lists to be the same, so let's start with the irons. On the right side, if I put a 3 here, this will make me have 3 irons, which is great. So let's fix the oxygens. Oxygens, I need 4. So I have to at least put what here times 1 to give me 4. Well, I need a 4 to fit here. But then that's going to change my hydrogens. Totally fine. 4 times 1 is 4 oxygens. 4 times 2 is 8 hydrogens. I messed up my hydrogens, but we're going to go back and forth. So come over back to the left side. How many, what number do I put here to give me 8? So what times 2 is equal to 8? If I put a 4 here, my 4 times 2 is equal to 8. And you can see that I have 3, 4, 8, 3, 4, 8. This is balanced. If you're balancing with polyatomic ions, do not break the polyatomic apart if it is the same on both sides. And so if we're looking at the this image here, we have this little phosphate hanging out right here on the reactant side. And you see how it's the same on the product side? Exactly the same. This phosphate here and this phosphate here, they're the same. So I can count them kind of as the same thing. So let's take a look here at this strategy. So we're going to start with our T-chart. And I'm going to place some markers in front to help me know where I'm going to, whoops. Okay. So I'm going to use my polyatomic as the same on both sides. See how I have PO4 on this side and I have PO4 on this side, and it's exactly the same, and there's no other phosphorus or oxygen on any of those sides, and so we can actually count these PO4s together. Now, you do not have 4 POs. If you have 4 POs, it would look like this. This would be 4 POs. But you have over on the left side 1 PO4, 1 phosphate. I have 3 sodiums, 1 phosphate, I have 1 magnesium, and I have 2 chlorines. So copy paste the order onto the right side. And I know it's a different order up at the top, but I'm telling you, if you have your order the same down here, it will help you balance it. So for sodiums, I have 1. For phosphates, now I have 2 phosphates on the right side. I've got 3 magnesiums and 1 chlorine. So I need to balance this. Let's just start at the beginning with the sodium. So I need 3 sodiums on the right side. So what is going to go here times 1 to give me 3? Stick a 3. So this changes my sodiums to 3, and it also distributes to the chlorine, making this 3 as well. Notice that I'm always changing a number up here before I change it down here. Now let's change my phosphates. I have 2 phosphates on the right side. I need 2 phosphates on the left side. So we're going to put a 2 here because 2 times 1 phosphate is 2. This is not 2 times 4, 8, because phosphate is PO4. This is 2 phosphates, and then 2 times 3 sodiums is 6 sodiums. Now let's, you can fix your sodiums if you want to. Let's fix the magnesiums next though. So I need 3 magnesiums on the left side. What times 1 is 3? Well, that is 3. 3 times 1 is 3, and then 3 times 2 chlorines is 6. And so I need to go back and change this number for sodium again, which is fine. Just erase it and put in the 6 that you need and continue your work. And now we have 6, 2, 3, 6, 6, 2, 3, 6, and this is balanced. So go ahead, and if you want to practice balancing some, these are multiple choice options. And here are the answers to those. Oh, no, they're there again, sorry. So we've got a few different types of chemical reactions. We're going to be going over this in lab as well. But you should know combination, combinations also known as synthesis, decomposition, single and double replacement, or combustion reactions. So here are the reactions that you should know. You should know that combination is also known as synthesis. And so I'll be using both, trying to reiterate that both are options. So combination reaction. A combination reaction is where two or more elements form one product. So look at all of these examples. They all have one product that they're being made. Yes, I know it's 2 moles of sodium and 2 moles of magnesium oxide here, but it's just one type of product. There's no plus sign on the right side. So no plus sign on the right side, you got yourself a combination reaction. You're combining to make one type of thing, even if you've got more than 1 mole of that thing. So that is a combination reaction. So here's an example, some images. You have magnesium and oxygen making magnesium oxide. Decomposition reaction is the opposite. You have one thing turning into 2 or more things. And so notice here the hallmark is we have one reactant this time, no plus sign on the left side. So these are decomposing. We see this mercury 2 oxide breaking down into mercury and oxygens, decomposing into its elements. We have a single replacement reaction as another option. You have one element that's replacing another element. So we have here B and C are chilling together. So here your hydrogen's hanging out with your chloride, the copper's hanging out with sulfate, and then we have the single element, zinc and iron, that then replace the hydrogen and the copper to hang out with the nonmetal. And so A replaces B to make A and C together, and B is kicked out on its own. And so we kick out the hydrogen. When it becomes on its own, it bonds with itself. And then when we kick out the copper, it's just neutral, regular copper on this side. So here's an example of some single replacements happening. You will typically see bubbles being made if you do acid, because look at what I'm making. I'm making hydrogen gas. Of course, I'm going to see some bubbles here. So the zinc is turning into zinc ions. So that's kind of, the zinc is dissolving. Okay, it's turning to aqueous ions. And your hydrogen is turning into a gas. But notice that the chloride stays exactly the same. Nothing is happening there. It's just who it's partnered with, I guess, is a little bit different. Then you have a double replacement reaction. There's no one that's single. Everyone has a partner in the end. It's just a new partner than it was before. So we're kind of just doing a little switch and a little swap. So you have your metal. It's going to hook up with your new other nonmetal. So silver is going to go with chloride, and sodium is going to go with nitrate. So you see that happening here. And the textbook does a good job of showing you these different colors. So here's an example of this. I make a solid here. It's called a precipitation reaction. That's a double replacement. Lastly, we have a combustion reaction. A combustion reaction is carbon containing, burning in oxygen to make carbon dioxide and water. You need to know combustions are carbon compounds plus oxygen make carbon dioxide and water, and it's all gas. The products here. Why is the water a gas here? Well, because a combustion reaction has a lot of energy that's released, so the water doesn't stay liquid, it's a gas. And so incomplete combustions actually give us not very great things like carbon monoxide, so you have to be very careful when you're burning things in your house, because you can make carbon monoxide. Your car exhaust has carbon monoxide in it as well. So here's some other information about carbon monoxide if you are interested in that. It competes with oxygen for in hemoglobin. So here's information more about hemoglobin. What happens is that the oxygen is supposed to bond with the iron in hemoglobin, and so it like oxygenates the blood, and the oxygen is carried around through the blood because it's bound to the hemoglobin. But when the carbon monoxide is like in competition with the oxygen, if you have too much carbon monoxide in the air that you're breathing, then your lungs don't get that oxygen, and your body, your cells don't get that oxygen. So you can have some of these symptoms. Here's a little summary table of those different types of reactions. Let's get some practice in. So pause and tell me what kind of reactions these are. So reaction A, I see here that I have something single in the beginning. And this something single okay, sorry about that. So something single in the beginning should make me think single replacement. Make sure that it's replacing. So we have the hydrogen here with the sulfate here. The aluminum is coming in. It's hooking up with the sulfate, and the hydrogen is getting kicked out. So we see the hydrogen by itself on the right side, and the aluminum with the sulfate over here. So we have aluminum ions with the sulfate ions. So what's happening to the aluminum? It's going from neutral to an ion. The sulfate is not changing. The hydrogen is going from ion to gas. So this is a single replacement. You can designate that SR. For the second one, we see there's no singles, but we do have some things happening, right? And so you can notify this as a double replacement because you have your sodium hooking up with your nitrate, and you have your silver hooking up with your sulfate. So pause and look at this one. And for this one, I have two things coming together to make one, which is a synthesis or combination. The opposite of this would be decomposition. And then in the second one, we have a combustion. Carbon reacting with oxygen to make carbon dioxide and water vapor. So this is your combustion reaction. So go ahead and give a pause. Give me one last check. And here are the answers to that one, making sure you have those. Okay. That is going to be the end of this part 1 video. We're going to pick up with a part 2.